So I wanted to give a little bit of introduction of myself before I launched into this. Yes, I am a scientist on the MAVEN mission. I'm also a faculty member in the University of Colorado in the Department of Astrophysical and Planetary Sciences. University of Colorado is a real powerhouse academically in the space sciences, and our particular department has coursework, advanced coursework that is absolutely unbeatable. In fact, we call it Starfleet Academy. Any of you that live in the Boulder area, there's frequently the opportunity to take our classes, even not for credit. Many of the faculty members will allow you to sit in on courses, and they're absolutely dynamite. Our department is also the sponsor of the Summers-Bosch Observatory, and every Friday night we hold public houses, and you're welcome to come look through our telescopes, hear the stories about what's up in the sky. We're also the proud owner of Fisk Planetarium, which is undergoing a multi-million-dollar makeover and due to reopen in October. Amazing digital projection on the dome and a wonderful star projector as well. So be sure to keep an eye out for that. I'm also a member of the Laboratory for Atmospheric Space Physics. This is one of these buildings out in East Campus. LASP is one of the few organizations in the country, on the planet, that is capable of conceiving and building and then operating space missions. It's really the ideal job for me to be here and work both on the academic and the research side. The last thing I wanted to say about myself is that I'm the co-author of a textbook. If you want any of the scientific background behind what I'll be talking about today, you could go downstairs, the bookstore will be open, and get a copy, but it's actually, you should just go buy a used copy or find one that the student has left on a desk somewhere. So I'm a faculty member now, but it wasn't always my dream to be a professor. I'm a child of Apollo, and so when I was growing up, I couldn't believe the space race that song epitomized so well. And in fact, I was so enthralled with the space program, I said it would be enough for me just to be a janitor for NASA. And now that the university has me empty my own trash, I guess you could say that part of my dream has come true. I got a little bit older, and like many of you, I said, I want to be an astronaut. How many of you wanted to be or still want to be an astronaut? And I went down that path for a while, and then I got some wisdom. Somebody said, well, you want to be an astronaut? What do you want to be first? A scientist is what I wanted to be first, and it's what I am, and it's what I absolutely love doing. Surprisingly, the astronaut corps didn't need me, but I'm extremely happy doing what I'm doing now. I wanted to find out a little bit about you also. How many are from Colorado? Boy, that's everybody in this side of the room, so I didn't know the seating was segregated. But those of you who, welcome to our state if you've just come here. Those of you from Colorado, I wanted to say I'm talking about the MAVEN mission, which is nearly 100% Colorado born and raised. We conceived the mission here, we're building most of it here, and we're going to operate it from Colorado, and so we can take great pride in that. So my purpose today is threefold. I want to talk about Mars as a world that may once have been habitable and show you or remind you of the evidence for this. I'll give you the rationale for the MAVEN mission, and you can see there the clunky acronym, Mars Atmosphere and Volatile Evolution Mission. I'll explain how we designed and conceived it. And lastly, I'm going to show you some really great pictures that show what it takes to actually build and test and prepare a spacecraft like this for launch. Now, I think everybody in this room knows that this is just one in a long history of Mars missions. And so it's my purpose today to explain why we need one more and why specifically we need the MAVEN mission, what it does that's different from every mission that has come before. And I think you also know that this is a risky business. And in fact, well, you see the X showing up there. That mission to Mars failed, and so did that one, and that wasn't looking so good. Well, we had a few successes. Well, the scorecard is not looking too good for getting spacecraft to Mars. And in fact, the statistics are Earth 16, actually that should be 7. No, I have Curiosity, 16. And the Mars Imperial Defense Grid is 22. So these are the odds that we've faced with the MAVEN mission. Nonetheless, we're going with Lockheed Martin. They've gotten many spacecraft to Mars, and we're going in with great confidence. So the first part of the presentation is to talk about Mars today and Mars yesterday. And many of you have, I'm sure, followed all the latest discoveries of what Mars looks like today. And you know that a lot of the major features include volcanoes, Olympus Mons, tallest volcano in the world, Valles Marineris, longest canyon, in the solar system. And incredible features of polar caps, where the major ingredient of the atmosphere freezes out on the surface every winter and sublimes away every spring. Some surprisingly active geological features, especially those that are wind-driven, the formation of dunes and dust devils, as you see here with a shadow cast on the surface. And of course, a lot of that leading to incredible dust storms, leading then to incredible erosion on the surface. So anybody who read with interest about these opportunities to go to Mars on a one-way ticket, this will be your home. Did anybody actually sign up for those tickets to Mars? Good. Best of luck to you. Don't forget to write. And we hope you enjoy your new home. It's truly remarkable, the images which are sent back from the surface. And not just from a scientific point of view, but from the ability to visualize what it would be like for us to be there as well. I guess the other story I forgot to tell about myself is that when I was in my astronaut phase, I said I wanted to go to Mars and raise chickens, because I wanted to find out if chickens would be bigger in low gravity. And apparently I'm not going to get this chance, but maybe my kids will. So now I want to start showing you the parts of the surface of Mars that say something was different billions of years ago. And it gives such pleasure to show these pictures, because it doesn't take anything more than common sense to look at these and perform your own geological interpretation. Here's the surface with a river valley on it. These channels are collecting together to let water, probably from ancient rainfall, flow downhill. There are other features that look like sediment deposits, and some of those sediments get eroded away and leave this geology that, for the life of me, looks just like features you might see in Utah. And so these are the features that actually make Mars, from a landscape point of view, perhaps closest to Earth of any other place in the solar system. This is showing you the landing site of Curiosity, and this crater which is filled in. This is not one of those deep craters that we've come to be accustomed to elsewhere in the solar system. This was filled in either by wind-blown dust or by dust deposited in water. This is a site of ancient flash floods. All these jumbled rocks were displaced thanks to the motion of incredible flash floods. And here, a view from Mars exploration rovers showing you the wall of a crater. And some of these minerals I'll describe to you shortly, again, on a very small scale, give evidence of a very different Mars in the past. I want to guide your eye a little bit more in understanding some of these geological features, so that we're all led to the same conclusion. This is not Mars, this is the Moon, and you can see a lot of these craters. They can be they can be bowl-shaped, deep in the center. They have raised rims, and these are the hallmarks of a surface which has been unchanged for billions of years. Almost all these craters formed 4.5 billion years ago, or at least 4 billion years ago. And that's the context of all the planets, all the rocky worlds in the solar system, heavily cratered. And only if something interesting has happened after that, other geological activity like erosion or volcanic activity in the case of the lunar mare here, only under those circumstances do you erase those craters. So with these eyes trained on the moon, I want you to look at this picture of Mars and appreciate, again, a lot of these subtle features here, which are river valleys connecting together. And look also at some of these craters. Some of them are deep and bowl-shaped with raised edges. Others are virtually completely eroded away, some of them almost completely filled in. These are the signs of ample erosion in the past, and the photogeologists that have studied this attribute the softening of this terrain to rainfall. And so I want you to go back billions of years and imagine a potentially habitable Mars with rainfall. Many of these river channels you could walk in nowadays, and they would look like some of the dry riverbeds of the Southwest. In a lot of ways, it makes geologists very wistful to see this landscape, which is so completely dried up nowadays. So the evidence from space, from orbit, clearly says that there was ample water, probably flowing water, possibly rain, that would have contributed to habitable conditions back then. And you need to be thinking about how uninhabitable Mars is, especially how cold it is, and what it would take to make that planet warm enough for this kind of activity driven by water. So the picture from the rovers is also clear evidence for the action of water on the surface. And you've probably seen this picture from the Mars exploration rovers climbing up and down this crater wall. You can see the tire tracks here. The analogies with the American Southwest is again strong, where you can see tire tracks in the desert. And these little divots here are where the drill has operated. And all of this light blue material here are these materials called blueberries, hematite, a mineral that forms in the presence of water, in this case, excuse me, percolating through rock and then being eroded out. And why do we think we know so much about these? Well, this is Utah right here, minus the tire tracks. And if you picked one of these up, you would find it's made out of hematite. These blueberries occur in the Utah desert as well. This is one of my favorite Martian pictures. I showed this to a group I was speaking to in Birmingham, Alabama, and I just put it up, and I didn't even tell them what it was. And somebody in the audience said, "That's a river delta, isn't it?" They know river deltas down there. This is flowing into a crater which is nearly the size of this room. This is one of the valleys that I showed you before, and all this material is being deposited as the water slows down and leaves the sediment. And it's color-coded for the kind of mineral. And in fact, the green that you see here is clay. Clay is another mineral that forms in the presence of water. And again, on both a geological scale and a mineralogical scale, the evidence of water in the past. And so the space artist who's featuring a new book here at this conference, Mike Carroll, did this illustration years ago, taking the current Mars landscape and saying what would happen if we added in water and atmosphere. And I think it's a great reminder to all of us that ancient Mars was almost certainly very different. So what could have sustained this early environment that was warm enough to be wet, and then even, well, wet enough to be wet? One of the best guesses is that there was a greenhouse effect which was far, far stronger than today. And the calculations, a little too small for you to read, I apologize, say that it probably needed an atmosphere that contained more gas than Earth does today, maybe 3 times more gas than Earth does today, even though Mars has less than 1% of Earth's atmosphere nowadays. So what this means, according to this theory, is that Mars has lost 99% of its atmosphere, maybe more. And so this is the driver for the MAVEN mission, is to figure out where that atmosphere went. So you kind of have two choices if you're wondering where the atmosphere went, where the oceans went. It can go up or it can go down. Although I went to a school group and posed this same question, where did the atmosphere go? And one kid piped up and said, was it the Martians? Did they drink all the water and breathe all the air? So we're not going to test that hypothesis, interesting though it may be. What we're working on actually is the ability to test the hypothesis about where the atmosphere disappeared to. For those of you who might know about, oh dear, I hope I haven't misplaced my favorite possession here. Uh-oh. What I've lost is a rock. That rock, wait, I don't think I've lost it. Here we go. Picked up from the side of Highway 36 this morning. Earth's volcanoes spat out all kinds of water, all kinds of carbon dioxide, so much carbon dioxide that if it stayed in the atmosphere, we would be as hot as Venus, maybe even hotter. Thankfully, that didn't happen, and the carbon dioxide in our atmosphere combined with eroded minerals and made limestone. So on Earth, this is where much of the atmosphere that came out of the volcanoes went. And so this rock is, well, it's worth its weight in carbon dioxide because that's where it has ended up. So after the early evidence arrived for Mars being warm and wet in the past, everybody said, show me the limestone. And so mission after mission went with instrumentation more and more finely tuned to find what are often called carbonate rocks, obviously related to their abundance of carbon dioxide. And they did find some, and in fact even some of the meteorites that come from Mars have had carbonites identified in them. But it turns out that the amount that they've discovered so far is minuscule compared to the amount which would be necessary to explain the loss of an atmosphere, 99% of an atmosphere made mostly out of carbon dioxide. So if it's not down, then the alternative is up. And the spacecraft orbiting Mars nowadays, in the case of the diagram on the right, Mars Express, is actually able to detect gas escaping away to space. The catch is that it's very hard to know what the total amount of gas escaping to space is. But this is the theme behind the MAVEN mission, and I'll remind you that NASA philosophy has been to follow the water, and you can see its connections with all those aspects of our interest in Mars there. So we've been following the water, following the escaping atmosphere, and where the heck is it? We don't know. And the latest evidence suggests that it's not, in fact, the water, there's not enough of it frozen on the poles to explain a potentially watery past that you see right here. The atmosphere cannot have been sequestered away in the underground. And so the leading possibility for where Mars lost so much atmosphere is that it escaped to space. I'm going to teach you a little bit of planetary science now and remind you that distance from the sun is one of the most important factors for determining what happens to a planet's atmosphere. It might be frozen on the surface, it might be vaporized and escape away to space if it's very warm. Mars is not close enough to the sun for that to happen very easily. The other factor which is really critical for the behavior of a planet's geological history, atmospheric history, is its size. And large planets stay warm inside, they have lots of geological activity, their volcanoes spit out a lot of gas, and their gravity is strong enough that they hold on to that gas. And the opposite of all those is the case for small planets. They don't make a lot of atmosphere, and it's easy for those worlds to lose an atmosphere. Mars, of course, is a medium-sized planet and sort of on the edge. Let's talk about that. Early Mars almost certainly, well, we've seen the volcanoes, it would have been warm inside, lots and lots of volcanic activity, lots of gases being pumped into the atmosphere. It also was the case that its core would have been very hot, convecting, churning around, and that would have given rise, a little hard to see under this lighting, to a magnetic field. A magnetic field which is so strong that it makes this protective bubble that particles from the sun, the solar wind, are in fact diverted around Mars. But Mars is a middling-sized planet. It did cool. Its volcanism is mostly stopped, probably not entirely, but its magnetic field is most definitely gone, except for tiny, tiny traces near the surface. So with a lack of volcanic activity, not much atmosphere is being regenerated, virtually none, and the loss of atmosphere for a number of causes, especially the solar wind, is substantial today. And the loss of the magnetic field is really central to this explanation. This is the backdrop of what the motivation for the MAVEN mission is. The MAVEN mission is basically designed to test this figure in the textbook. Is it really the case that Mars today is so exposed to the solar wind and other influences, combined with its low gravity, that it could have lost 99% of its atmosphere? So let me tell you about how the MAVEN mission is designed to answer this question. You can see our proposal submitted in 2006. So we've been at this a while. And we have a mission which is designed to study in detail what happens when a stream of charged particles interacts with the atmosphere and tries to drag away the ingredients of that atmosphere. So we're going to study the atmosphere as we see it today. We're going to see how much the rate of loss of the atmosphere is nowadays, and especially how it depends on the behavior of the sun. I think you know the sun goes through cycles. We're going through a pretty wimpy solar maximum right now, but we will see solar activity, and when the sun is in its most active phases today, it then resembles the situation of billions of years ago when the sun itself was more active. So our spacecraft is shown here. We've got big solar arrays and antenna, and it's bristling with scientific instruments that's capable of discovering all the ways that Mars' atmosphere can escape. So we are the size of a school bus and much prettier. And we are the mass of a heavily loaded SUV. And the details, what you might call the mission architecture, has us launching 3 months from tomorrow, not that anybody's counting. And we take about 10 months in our orbital cruise to get to Mars. This is the date that we arrive at Mars. We have a bunch of checkout to happen, and then we do 1 year of orbital observations at Mars. That's 1 Earth year. We're trying to get NASA a little confused on this. Was that 1 Earth year or 1 Mars year? So if we're fortunate, we'll go a little bit longer than that. So we're not a rover, we're not a lander, we're not bristling with cameras to take incredibly sexy pictures of the surface of Mars, but we're perfectly designed to answer this fundamental question of where did the atmosphere go. And in addition to our operation at Mars, people are going to be very busy down in Waterton Canyon, South Denver, operating the spacecraft there, and out in the research park on East Campus of University of Colorado, we're going to have a fleet of students operating the instruments. This is another thing that University of Colorado does, is train students to operate spacecraft. They go off to Jet Propulsion Lab and the aerospace industry. So how can a spacecraft figure out what happened on Mars billions of years ago? What we do is study all the ways that the atmosphere can escape. I'm not going to go through this very complicated diagram other than to say we have nailed down the different processes where the sun might influence the atmosphere to escape. just by heating or by sending charged particles plummeting into the atmosphere. Every conceivable way, we've studied how it can be measured. And each of these escape paths, we call them, can be quantified by these different instruments here. Our spacecraft actually dips down into the atmosphere, the upper layers of the atmosphere, and many of our instruments are designed to basically sniff the properties of the atmosphere there. How many carbon dioxides, how many oxygen atoms, how many hydrogen atoms. We can count them. We can see how energetic they are. Do they have enough energy to escape? How high do they extend? Are they on their way to escape from Mars? And so the mission is perfectly designed to quantify all those different paths to escape. So if you're going to have a spacecraft that's it's basically $500 million and it's got about 9 different scientific instruments on it, how do you know you're doing it right? And the answer is reviews. Our mission, every NASA mission, undergoes extensive reviews. And so 220 times since the mission was approved, the key people gathered in a room and were examined by the panel of experts. It only happens on days that contain the word day. It was a grueling process, but it ensured that we had a good chance of success. So we're going to spend just a couple of minutes talking about my baby, the imaging ultraviolet spectrograph. Isn't that a beautiful name? This is a device that costs about $22 million to build and operate. And it samples it studies the atmosphere not by smelling the atmosphere locally, but by looking at a distance at the ultraviolet light which is given off by the atmosphere. Earth's atmosphere glows in the ultraviolet. Occasionally it glows even at light that we can see through the process of aurora. All these processes are occurring at Mars as well. And the Laboratory for Atmospheric and Space Physics has sent ultraviolet spectrographs to every planet in the solar system. Well, we can say that ever since the demotion of Pluto. All the other planets we have sent our instruments to. And what these spectrographs do is divide up the spectrum of ultraviolet light in a way that we can identify what gases are present. Every gas has its own characteristic wavelengths of emission of light. So if we see light at a certain wavelength, we know that's a hydrogen atom. At another wavelength, we know it's a carbon monoxide molecule. And so from a distance, we can basically figure out what the atmosphere is made out of. And we're able to scan low and high in the atmosphere and figure out how much of these different ingredients there are at different altitudes. And those of you with sharp eyes might notice that the heavy stuff doesn't go very high, but the light stuff, hydrogen, goes way high up. An indication that hydrogen is going to be a gas which is easy to escape. A deeper look at this shows you that how fast an atom or molecule goes depends on 2 things in an atmosphere. It depends on how heavy that particle is and what the temperature is. And so there's an equation, there it is, won't be on the test, that says that if you're very hot and very light, you're going to go very fast. Now, the air in this room is moving at about 500 meters a second. Just gestate on that for a bit. And that's heavy stuff like oxygen and nitrogen. When you think about hydrogen on Mars, it might be going several kilometers a second, and that's enough for it to escape. So it's very likely that those ancient oceans were broken down into hydrogen and oxygen, and were able to a lot of the hydrogen probably escaped away to space. Now, oxygen is pretty heavy. It can't escape. Maybe it was carried away by those solar wind interactions. We don't know. Anybody think of another good place for oxygen to go to on Mars? Up or down? I think I heard rust. Yes, the red planet, that used up an awful lot of the oxygen. but almost certainly there needs to be another process that gets rid of even more, and we think it's related to the solar wind. Now, one of my favorite parts of our instrument on the MAVEN spacecraft is a special channel. We flip in a special optical element, and we're able to see the difference between regular hydrogen and heavy hydrogen, which is called deuterium. Picture an ocean of water on Mars, broken apart, some small fraction, excuse me, some small fraction of those hydrogen molecules have an extra neutron. Our instrument is so fine-tuned that we can tell the difference. Now remember the other thing that I told you, which is that heavy stuff escapes more slowly than light stuff. If you have, start with a certain mix of hydrogen and heavy hydrogen, the heavy hydrogen is going to lag behind. And the amount that that ratio gets skewed tells you actually how much of the atmosphere, how much of the hydrogen has escaped overall. So look for our discovery in months after launch, we hope, that shows how much of the ocean would have been lost to space through this process. So I'm going to end with a handful of pictures that try to make this MAVEN spacecraft a reality for you, and not just a bunch of PowerPoint slides. This is our instrument. Boy, I sure hope they take these lens caps off before we launch. Bright colors, little flags on them. You know, they don't want to miss a beat. They actually let me into the clean room. I'm the handsome one right here, and there's our instrument right there. People sometimes ask me if I'm a rocket scientist, and I'm, well, kind of. And then I was put in place by somebody who said, I would never get into a rocket built by a rocket scientist. A rocket engineer, sure, but rocket scientist, so put me in my place. I'm not the person that built this, but I did give the ideas for how to do it. I got to visit the spacecraft as well while it was being assembled. Doesn't look like much yet, but it was pretty amazing. This is a NASA administrator here, and everybody is making sure that all of our questions are being answered. But I can't take my eyes off the spacecraft, and I'm saying, wow, it's really not just PowerPoint anymore. So just to continue in this sense of making this a more real mission to you, they have this amazing lightweight structure here that holds all of our instruments. This is this is where they put the explosives. We have incredible retro rockets on board to get us into Mars orbit. We need solar arrays there to have enough power, and you can see the scale of these. They're a little bit tilted here. We call it a gull wing design because we actually fly through the atmosphere, and we want to make sure that we maintain the proper orientation. It's got a nice big antenna on board. Every 3.5 days, our data comes pouring back to us, and we'll be sitting in our computer terminals eager for the data. And this is part of the process where they're tacking on all the different instruments, all those things that measure the different processes of escape. It starts to look more and more like what we envisioned for the complete device. They test everything, and in fact, this was the day that they tested the deploy of the solar arrays, which are stored like this in the spacecraft fairing, and they had to support the weight because the spacecraft is not designed to operate in 0G. Just a few more pictures that show all the different ways that they test it. They attach it to a table here that can shake the whole spacecraft to about 20 Gs, which is comparable to the environment it experiences on launch. And that, number one, they want to make sure that no part of your instrument or component falls off and stops to function. They also want to make sure that nothing's going to fall off of yours and break something else. So it's very heavily tested. They do a deep test for electromagnetic interference so that when one part of the spacecraft is operating, it doesn't affect another. And They put it in a chamber that they can remove all the air from to simulate the vacuum of space, and they crank it to the lowest temperatures and the highest temperatures that the spacecraft is going to experience and make sure that everything works under those conditions. Really impressive, the facility that Lockheed Martin has to design and test this. Here's the scariest test from my point of view. They need to know that we will be able to measure the magnetic field on Mars. This is a critical quantity for the interaction of the solar wind, which is controlled by magnetic fields. And to make sure that we have no stray magnetic fields on the spacecraft, they have a whole bunch of magnetic sensors mounted around this, and they swing our spacecraft ever so slightly past these sensors, so we know exactly the magnetic behavior of our spacecraft. The whole spacecraft is held by this, this one link right here. This has to be the scariest day in the life of the spacecraft, held just by that one connection. We'll be launching on an Atlas V. It's going to look a little odd because there's one booster strapped to the side. You can imagine the big rocket and a little rocket on the launch pad. I'm sure they've figured it all out. Getting ready to ship down in South Denver. They crated it up. It fits into the back of a cargo plane. It's arrived at Kennedy Space Center. And the summary is that things are in really good shape. Not only are we on schedule, but we've matched the budget that was assigned to us by NASA. You've probably heard that other missions struggle with this, but thanks to our principal investigator, Bruce Jakosky, and the expertise of Lockheed Martin, we're in very good shape. And this is a diagram from our proposal from 2006 that said when we wanted to be done. We haven't had to change this diagram other than moving this arrow over to the right. So I want you to link these things together, that we have a spacecraft conceived, born and built and tested in Colorado, and it's going to go to Mars today to try to envision what Mars might have been like billions of years ago. So the last thing that I wanted to leave you with are ways that you can keep up with us, keep in touch with us. And there's a website listed here on the top of the screen. It won't be hard for you to search for this if you don't write it down. You have about 2 or 3 more weeks to send your name to Mars. Has anybody already sent their name to Mars? I hope everybody in this room can travel along with us vicariously and have the thrill of arriving at Mars in just over a year's time. This also has all the ways to follow us on Facebook and Twitter, and we'd love to have you come along with us. That's all. Thanks for your kind attention. Let me close by saying that I have a few MAVEN goodies, and if you follow me to the back of the room after this, I'd be pleased to give them away, one a person, unless you will give them to kids who might turn out like, well, you never know. Okay, thank you. Oh, how to distinguish between hydrogen and deuterium. So chemically, they are indistinguishable. You can have H2O, or you can actually have HDO. So chemically, they're extremely similar. But the heavy molecule actually emits light at slightly different wavelengths. And so it's awfully small, and quite frankly, that's why our instrument costs $22 million. With a prism, the rainbow is spread out this much, and with our expensive grating, it's spread out this much. The tiniest fraction, 1 part in 1,000, we can tell.
Yeah, who made the grating?
The grating, I ought to know this, but I've forgotten. I apologize. It's called an Eschell grating, and it's a technological marvel.
Yes, first, thank you very much for this very, very instructive presentation. You have answered so many questions one had about, what could be the past of Mars, that I'm asking an indiscreet question. How much of that is scientifically shared by your colleagues?
I have given what you might call the majority view in planetary science about a warm, wet Mars in the past. There are minority views which I respect. This is how science works. People say, it could be like this. The two major competing visions with this are the following. One is that Mars was warm and wet, but only right after an impact levitated an awful lot of frozen material into the atmosphere, a temporary atmosphere. Some people think it might have been as little as hundreds of thousands of years, this warm, wet period. Others argue that those geological features can't be carved in that time. The other competing theory is that, yes, it was warm and wet, but so salty and so acidic that it would not have been habitable. And even the Mars exploration rovers were getting some evidence of that the conditions were warm, wet, but not habitable. Curiosity, however, with some of its discoveries, their statement was, this is water you could drink. And I think you'll have some other investigators later today from Curiosity. You can ask that question. So that theory of inhospitable Mars may be on the decline.
Thank you very much. You seem to have the best job in the world. I have a question. I don't know how to ask it. The data will come in, and you as a scientist, will you know right away that it might be correct that 99% of the atmosphere has been lost? Do you have any numbers in mind? Or will you have to do a long analysis and have a lot of statistics and graphs and then say maybe, or?
So it's going to be more like the second case that you described. You know, we feel we're in a tough spot because every other mission lands on Mars and it's got a picture on day one, wowie. And we're going to go into orbit and say, not yet, we need to make some more measurements. So more like maybe even the full year before we can assemble the picture.
Okay, in the
It's
back.
not as easy as taking pictures.
Yep, go ahead.
I would like to know more about the magnetic field and atmosphere. I was wondering how the Mars could reduce the magnetic field, and also how Mars could atmosphere lose completely or not.
So you were asking about how Mars could lose its magnetic field and lose its atmosphere?
Yes. Second question is if Mars could lose atmosphere completely or not.
Sure. I want everybody in this room, as you take a breath, to appreciate the existence of our magnetic field because it actually stands off this solar wind which could strip away components of our atmosphere. Mars had a strong magnetic field in its past. We know because when you fly a spacecraft low over the surface, there are remnant magnetic fields that show that it was very strong in the past. And we also know that magnetic fields are created in the interior of a planet when molten metal is convecting and the whole system is rotating. Whoever figures out really how magnetic fields work will get a Nobel Prize, so maybe this will be inspirational to you. But we think that Mars' core cooled off and it doesn't do that convection anymore. And we now know from spacecraft flying around and around that the magnetic field is virtually gone. So this is not a theory about the presence or the disappearance of magnetic field. It's borne out by the data there. And because the magnetic field is so important for keeping this breeze of particles from the sun away from the top of the atmosphere, when you lose that magnetic field, we're going to test the hypothesis that you can lose the atmosphere. I don't mean to say we know now that this process got rid of the atmosphere. If we knew that, we could have saved $500 million. We're testing that hypothesis.
Okay,
you
I
so
think that'll
much.
have to be our last question. Thank you, Dr. Schneider.